So those are the expression for the first order energy correction and the second order energy correction. So we have expression for the energies, we have expression for the first and second order Hamiltonians. And now we remember that we defined properties as derivatives of the energy. So derivatives. And for example, we had defined a dipole moment as the first derivative of the energy with respect to some field. So we had a derivative with, let's say some component alpha. If you have the energy in the presence of the field. And later on, we evaluate this derivative for zero field strength in order to get the permanent properties and not some induced ones. And now if we use, that was sort of was our definitions of the properties, and now we want to use perturbation theory. And in perturbation theory, I mean, we expand the energy in the unperturbed energy plus a first order correction plus a second order correction plus a third order correction and so forth. And the first order correction being first order, having the first order Hamiltonian in there, means it's those kind of terms here which are all linear in the perturbation. Therefore it's first order. And the next one are the ones which are quadratic in the perturbation, or bilinear, which sort of form quadratic. Now, if I take the derivative, first derivative with respect to some of those fields, then of course all the terms which are linear in the field disappears from that term, and all the terms which are quadratic in the field, they still are then linear in the field if I take the first derivative, because the derivative for x squared is 2 times x. But if I then evaluate afterwards that derivative for zero field strength, then all the terms which still depend on the fields, they all are set to 0, because I set the field to 0. And that means if I take this derivative and evaluate at zero field strength, I actually only have to look at the first order correction to the energy and take the derivative of that with respect to the field. And essentially, actually, I don't need to set the field afterwards to 0 any longer, because the first order correction only is linear in the field. If you take the derivative, then they disappear. Of course, in a way I should do, and this here is in a way in quotes, because what I have to set 0, I have to set 0 all the other, I mean all the fields and all the perturbations I have. So if I have a magnetic moment and a magnetic field there, and if I take the derivative with respect to the magnetic fields, then I of course also have to set 0 all the magnetic moments and so forth, all the perturbations. And that means then if I take this expression here, that's my first order energy. So I take the derivative of that. So it's the derivative with respect to the alpha component of the field of my first order energy. Like this. And then if I insert my expression for the first order Hamiltonian, and let's write it in a general way. Just write it as one of those operators P, vector operator, times a general field or magnetic moment, whatever it is. Could be electric, could be magnetic, could be field, magnetic moment. Then this is a zeroth order wave function, so this is an unperturbed wave function. That does not depend on the fields, because it comes from the Schrödinger equation where there are no fields. So if you take the derivative of this, I mean the first thing I have to do, I have to move it into the integral. Otherwise I can't do anything. But that integral here, that's an integral over electronic coordinates. The 3n electronic coordinates plus the n spin coordinates of the electrons. This is a derivative with respect to a field, which means a completely different variable. And if the variables are different, then I'm allowed to interchange derivation, derivatives and integration. So I can move it in, and then, although we write it here in bracket notation, still this is a product of three things. It's this function complex conjugate times that operator acting on this function. So I have a double product, and I have three things which are multiplied together. And in principle, and later on, I think in the third hour today, we actually have to do that really, and have to use the product rule all the time. But this one is not depending on the field, this one is not depending on the field, so the only thing which depends on the field is this one. So we take the derivative of that, and this is a scalar product. So it's px times fx, py times fy plus pz times fz, and I take the derivative with one of the components. So the other two terms, they disappear because they don't depend. If that's the x component of the field, the term which has the y and the z component, they obviously don't depend on the x component. So the only thing which I get out is psi 0, p alpha, psi 0. And you can see that is in very much the motivation for writing the Hamiltonian out like this. Because then it's very easy to take the derivatives. Because I've separated them in either scalar products or in this kind of double scalar product or tensor products. So I can easily take the derivative, and what I end up with is matrix elements or expectation values here of these p operators, which are the part of the perturbation operator which depends on the electronic coordinates. Now let's take an example for that, and that, as I said, is the electric dipole moment. So an electric dipole moment, let's take again the alpha component of an electric dipole moment of a molecule. We really defined as minus the derivative of the energy in the presence of a field with respect to the alpha component of the field, and then, as I said, we evaluate to 0, and that gives us now here that derivative is basically what we calculated here, and that operator, I said, is the dipole moment operator. So that gives us and wait a second, here it is. That gives us then psi 0, p alpha psi 0. But that p for the electric field, that was minus the dipole moment operator. So we get psi 0, and then we get the electric component of the dipole moment operator plus the nuclear component of the dipole moment operator so it's 0. So we get that the dipole moment, or component of the dipole moment, is just the expectation value of the corresponding dipole moment operator. And I mean, how that dipole moment operator looks like, that in a way is determined by this derivation, what this PF here turned out to be. So that should be PF.